it's both easy and hard to introduce a local colleague. I'm going to err on a brief introduction only. You all, I hope, know Monika Schleier-Smith. Her labs are in Varian, and she's been with us for many years now. She's an atomic physics experimentalist, or quantum optics experimentalist, or maybe just a quantum engineer, we can call it nowadays. She got her bachelor's at Harvard and then moved very far to MIT to continue her work in physics with Vladimir Voltage, where she did some really foundational experiments in cavity QED and squeezing and all sorts of fun games with atoms and photons. After that, she did a fairly brief postdoc with Emmanuel Bloch, working with optical lattices and many-body quantum simulation, and before coming here in 2013. So she's now an associate professor and has won many awards, so many I can't list them all, but I'll give you the highlights. She's won a P case, which is from the president. I don't know if you've met him, but some of us can with those types of awards. It's very wonderful recognition. An NSF Career Award, and an AFOSR Young Investigator Award, a Sloan Fellowship, a Hillman Fellowship, an award from the Research Corp. So it goes on and on. It's a very illustrious career.
Ben, we have a question here.
Yeah.
Which president?
I'm not going to go into any of that. We got P cases for different presidents, I'll say that. All right, so I'll hand it over to you.
Thank you. So to answer the question, it was this summer and the president did not attend. But at least they have a science advisor and they caught up on 3 years of issuing this award. So, yeah. Okay, so the title of my talk is Choreographing Quantum Spin Dynamics with Light. And it's a talk about some work going on in my lab where we are using light to control interactions between laser-cooled atoms, which I view as model systems for studying quantum mechanics. So in case anybody in the audience doesn't spend every day thinking about quantum mechanics, I need to start with the whirlwind tour of...
There is a funny glare that was...
There's a funny glare.
I'll work on the lights.
I need to... Okay, so while Georgia works on the lights, I will give a brief review of what is so special about quantum information.
You can't fix it. It's a problem in the projector.
Yeah.
What's that?
You cannot fix it. It's a problem in the projector.
Oh, great. It's very expensive. But it's a very expensive.
Okay. Hopefully the graphics are clear enough in any case. Okay, right. So what's so special about quantum information? We all know, right, in our classical computer, information is stored in bits. In quantum system, information can be stored in qubits. And this is partly a chance for me to introduce some terminology for the remainder. So, right, a bit is something like the orientation of some magnetic domain in your hard drive. A qubit for the remainder of this talk I will refer to as a spin, right? If it's pointing up, that would be kind of the one state. If it's pointing down, that would be the zero state. Okay, but what's kind of special about qubits is that they can actually point in any direction on the sphere, and I actually have to sort of measure the state to get a 0 or a 1, and when I do that measurement, there's going to be some randomness in the outcome, right? So if the spin is pointing up, I'll get a 1, if it's down, I'll get a 0, but if it's pointing somewhere in between, the outcome might be 50-50, right? Okay, so reading out the state of a quantum bit is a little bit like a coin toss. And so there's some probabilistic aspect of quantum mechanics. That's, a little bit weird. But what's really weird is this isn't just any old coin toss, right? So in quantum mechanics, you can have a situation where Alice is in my lab here in Varian building, and Bob is perhaps in Ben's lab over in Spilker building, and both of them are tossing these quantum mechanical coins. Alice gets some random looking outcomes from this probabilistic process. Bob also gets some random looking outcomes from this probabilistic process. But when they compare notes, they might realize that every time Alice got heads, Bob got tails. So what's going on here? So this type of thing is possible in quantum mechanics if Alice and Bob have qubits that are in a so-called entangled state. So in other words, in quantum mechanics, it's possible for the probabilistic behavior of 2 or more qubits to be correlated, for there to be correlations in the randomness. And what this tells us is that it's possible to encode information not just in individual particles, but in a way that is delocalized across, let's say, 2 buildings at Stanford, or more generally, to encode information in a way that is not in one place. Okay, so, Einstein famously called this spooky action at a distance. So what's so spooky about this, right? Why does this phenomenon of entanglement kind of bother us or not match our classical intuitions? Well, the key reason is that the way that we interact with the physical world, right? The way that we interact with the physical world is always local, right? Particles interact with other things that are near them. So quantum mechanics actually has this weird feature that information can be non-local, right? But interactions, according to the laws of physics, are necessarily local. So actually what I want to talk about today is, well, just to step back for one moment. So interactions are local, right? And that restricts actually the types of physical states that we find in nature, right? So, or even the types of states that we can synthesize in the lab. So here's a beautiful picture where atoms have been confined on individual sites of an optical lattice, and one sees them organizing themselves into some kind of a checkerboard order, heads, tails, heads, tails. And that comes about really from interactions that are local, the fact that atoms that are, if they are right on top of each other, they will interact. That gives rise to some kind of magnetic ordering in this case. So that those local interactions kind of govern the types of physical systems that we find in nature. What I want to talk about today is actually kind of what happens if you can go beyond this sort of natural scenario and start to realize that our interactions that are non-local, where things don't need to talk only to other things that are near them. Okay, so why might you want to do this? Well, why and how? Okay, so the how, I'll get into the details later, but generally speaking, what we're going to take advantage of is the fact that light travels very quickly and will allow us to generate interactions that, for our purposes, travel so quickly that we can think of it as almost instantaneous. And so it will allow us to generate interactions between atoms that need not be between atoms that are near each other. So atoms will be able to talk to each other with the aid of light. Okay, so why might you want to do that? I'll give a few examples from kind of 3 spheres of application. So one is as a mechanism for generating correlations, for generating this, for encoding information non-locally, because entanglement can be useful, right? Another reason why you might want to generate these non-local interactions is that they actually appear, despite sort of seeming unnatural, in conceptual models actually from a wide range of areas of physics, ranging from condensed matter to quantum gravity. Okay, so I'll give an example in that area later. Okay, and the third sort of area where these non-local interactions actually appear on paper is that there's a way of encoding actually technologically relevant optimization problems in the framework of asking what is the ground state of some collection of particles, of spins, with non-local interactions. So these are all places where non-local interactions appear. And to just be a little bit more concrete, I'm going to start by giving you an example from this bottom category, which is, I like this because it's the one that you're most likely to find if you are reading the news or surfing the internet, okay? So if you surf the internet, you can find websites of a range of quantum computing companies that say they are going to solve your optimization problems, such as optimizing fleet operations, delivering packages during the holiday season. I love this example. What is it that they're going to do to more efficiently deliver your packages? Roughly, these companies work with some physical system that actually does in fact consist of qubits. I won't go into details of these systems, but qubits which in some way are induced to have some graph of non-local interactions, okay? And when I sort of, first heard about these things, there are lots of questions actually about to what extent quantum systems even can provide an advantage in solving these problems, whether entanglement plays a role, can play a role. But one of the questions I had in my mind when I sort of first heard about these things is, how do you even map these real-world problems, like delivering packages in the holiday season, onto some sort of a graph of interactions between qubits? So I was actually really happy when I learned about an example that I actually could relate to. This is an optimization problem that some of you might actually have encountered if you have ever been on a backpacking trip with a partner. So the problem is you have a collection of items, and they all have different weights. And you want to each ideally carry the same weight, right? So you want to minimize the difference in weights between your two backpacks. Okay, so that's the problem. How might you encode this in a physical system? Well, let's start by saying if we put an object in Alice's pack, we'll represent that as a spin pointing one way. If we put the object in Bob's pack, we'll represent that as a spin pointing another way. But these spins have different weights, okay? So I'll say that the z component of the spin is, let's say, +1 if it goes in Bob's pack, -1 if it goes in Alice's pack. And the optimization problem is going to be to minimize some weighted sum of these spins, okay? So I can minimize that weighted sum, or I could minimize the square of the weighted sum. And all of a sudden, this looks like something where I have maybe a physical system of spins that can point in two possible directions. They have some interactions between them whose strength is governed by these weights, okay? It's going to turn out that the interaction graph would look something like this. It's not something that I can put on a lattice and have nearest neighbor interactions. It's going to be some very non-local interaction graph. Okay, so I was actually really interested when I heard this, because it turns out that precisely this type of a Hamiltonian, this particular spin model with this particular energy, actually exists and has been physically realized already in experiments with atoms interacting via photons in an optical resonator, which generates this non-local graph of interactions. And not only have these types of interactions been realized, they've even already been realized in a setting where they demonstrably give rise to entangled states. Okay, so finding the ground states of these models is potentially of interest for these optimization problems, for making your backpacking trip more efficient. The dynamics, so sort of turning on these interactions for an initially unentangled state and letting it evolve, actually the dynamics are already used to give rise to quantum states, in particular with useful entanglement for applications in quantum sensing. So actually, as a physicist, I have maybe a weird definition of useful. So let me just give you one example of what I mean. So what do I consider useful? So one thing that's useful, for example, are better tests of fundamental physics, right? So these laser-cooled atoms are actually used really in exquisitely precise clocks, for example, that are so precise that actually they can detect changes in elevation from gravitational redshifts of a few centimeters, and that are starting to be envisioned as potential instruments for measuring gravitational waves, for detecting dark matter. That's a dream that will require really pushing these types of devices to their fundamental limits of precision. And it turns out that one of the limitations on the precision is, in fact, that sort of coin toss. The statistical fluctuations of the coin toss actually limits the precision of these devices. Okay, so entanglement is a resource that can reduce those fluctuations, generate correlations that can enhance the precision of these devices. And there's sort of been a lot of progress over the past few years in a variety of physical systems, but particularly in these systems of atoms interacting with photons in optical resonators, in actually generating entangled states that have useful properties precisely for precision measurement. So here's a beautiful picture from the lab of Mark Kasevich, where the ability to let atoms interact with photons in the type of system I showed you a moment ago actually allows for generating a state where the fluctuations in the orientations of these spins, right? We have many spins. Here we're drawing actually the average orientation of the spins and the fluctuations around that. And by engineering non-local correlations between them, it's possible to reduce these fluctuations in a way that enhances precision measurements by a factor of up to 100. So there's actually a few different directions, though, in which this can still be pushed further. So one is sort of pushing towards the best absolute precision of these devices, which involves maximizing the number of particles with which one can work and the strength of the quantum correlations. One is pushing towards the fundamental limit, that's the red line here, of what's possible with entanglement, with this number of particles. And there are also directions that aren't even on this plot, like asking not just about precision, but about other figures of merit, like dynamic range of a sensor, the bandwidth of a sensor. And it turns out that if one wants to start pushing on all of those figures of merit, one might need to start even going beyond the types of entangled states that I've drawn here. So what do I mean by that? So this system of atoms and photons has been used to generate what I might call conceptually simple entangled states. So it's remarkable one can prove that thousands of atoms are entangled, but somehow the state is still simple enough that what I've done here is drawn some picture that represents the state of a large collection of particles, just in terms of the average orientation of the spins and the fluctuations around them. So one of the questions that I'll talk about a little bit today is, this is sort of, I'll call this useful but simple entanglement. What's much more common in nature is what you might call useless entanglement. So what do I mean by that? So generically, whenever I have some interacting system, correlations will develop between the particles, right? In some form that is usually not describable by a simple picture. Okay. So, and in fact, it's usually too complicated to even start to calculate generically the properties of such a system. And yet, in some cases, in, let's say, condensed matter physics, where the behavior of a material is governed by the interactions between the electrons, we can't calculate this from first principles, but there's kind of a dream of being able to start to learn about these systems by building simpler model systems with specified interactions that are simple to specify, but nevertheless it's not possible to calculate what will happen. That's the dream of quantum simulation, is to sort of engineer simple models and observe the outcome. So one of the questions that we've been asking about is, can we take sort of this toolbox that has already a strong track record in quantum control, making specified quantum states, and start to actually bring it, to turn it into a toolbox that can also be used in the realm of quantum simulation, building simple models where we nevertheless building simple models that give rise, nevertheless, to complex entangled states that perhaps, if we can start to understand them, will also be useful. Okay. So I sort of, just to draw a bit of an analogy, I view this toolbox sometimes as if I were an artist and my toolbox were my sort of paintbrush and my palette, and the sort of left side of this slide is when you're using the paintbrush to make something very specific. You have a picture in mind and you're going to draw it. The right side is kind of, you're going to just drop some paint in the water and watch how it spreads, and maybe you'll learn something, and maybe you'll even make something beautiful in the process. Okay, so actually, this is actually a bit of an analogy for a process, this dropping the dye in the water and watching how it spreads, that I'll call information scrambling. So the question is, the quantum analog of that spreading of the dye, right, is something like, imagine I have an interacting system of a bunch of qubits, and I encode some information locally in one of them. And I asked the question, how long does it take for that information to become completely delocalized over the entire system? Okay. So this is a question that was thought about by, I think, many who are here in the audience, Patrick Hayden, Lenny Susskind, Steve Schenker, in the context of actually trying to understand what happens to quantum information, what happens to information that falls into a black hole. And without going into detail, I'll just say that somehow the resolution, there was a problem that there was the concern that information might be lost, which is not consistent with the laws of quantum mechanics. And somehow the resolution is to think of a black hole as a quantum system that's strongly interacting such that information, it's not lost, but it exponentially quickly becomes diluted in correlations among its many degrees of freedom. So this idea that one can sort of think of a microscopic quantum model for this process of information scrambling sort of raises the question, is that something you could build and study in the lab, right? And if you want to do that, you'll run into immediately the limitation that typical systems that we find in nature or even engineer in the lab have these local interactions, right? So if I have a system of atoms and, for example, perhaps I trap them optically in some lattice where they can hop to neighboring sites or interact if they're on the same site, then I will have the problem that information will sort of spread according to what we call a light cone. So this is not the real speed of light, but some effective speed of light governed by the characteristic timescales for hopping in this lattice. And I will never see something where information spreads exponentially quickly across all degrees of freedom. Even in systems like systems of trapped ions, where interactions decay in some power law way with distance, there is nevertheless some kind of a polynomial shape that governs how fast information can spread. So one of the questions you might ask is there a way to build something in the lab where information could actually spread exponentially quickly across all degrees of freedom? Or where that light cone might have a logarithmic shape, or even break down entirely. Okay. So there are actually models that can be written down on paper that are understood to behave in this way. And sort of their key feature, so this is a model known as the Sachdev-Kitaev model. The key feature is that it consists of particles that can hop in some correlated fashion over kind of arbitrarily long distances in an entirely non-local way. When I sort of see this as an atomic physicist, the picture that immediately pops to mind is one of some sort of atoms in a lattice. This is actually a real picture of atoms trapped in an optical lattice imaged with single site resolution, and then the dream is that somehow they should be able to hop in some way that looks like this. But that's not physically possible with massive particles, right? They'll only hop to neighboring sites. So the neat thing is that actually we'll take a different approach, and it turns out that with photons, right, we're going to have a way of letting spin excitations hop over kind of arbitrarily long distances, okay? So we're not going to have massive particles hop, but we're going to encode, we're going to think of sort of an atom that has two spin states as a site. Spin up, I'll think of as that site being occupied. And our goal will be to let these spin excitations hop by mediating this process with photons that can easily travel over long distances. Okay, and so concretely, how might that work? So again, I'll sort of think of this a spin-up atom as an occupied site. And what I want to do is sort of just turn a spin excitation into a photon, which can be absorbed by another atom, right? So it's a sort of flip-flop process for the spins, or I can think of it as this some sort of a particle hopping from one site to another. Okay, and that will allow me, because photons travel easily over long distances, to sort of evade this requirement that interactions be local or the hopping be local. So the one thing we need to be a little bit careful about is that naively you might expect if the atom decays by emitting a photon, that photon could sort of scatter off into any direction into a sort of a 4 pi in any direction in space. And so in order to ensure that that photon actually is absorbed by another atom, we need to play a little trick, which is to put some mirrors around our system, okay? And then we're going to have constructive interference that enhances the probability that a photon emitted by one atom will interact again with another atom. So that idea of having photon-mediated interactions is actually used in a variety of different physical systems, both in the microwave domain and also in the optical domain. And I've just shown a few examples here, ranging from superconducting circuits to nanophotonic devices to these kind of macroscopic resonators formed by a pair of mirrors end-to-end, like the one I'll show you in a moment in our lab. And depending on your application, these on the left are sort of used for quantum computing. The nice thing about these atom resonator systems, and the one thing that I think is sort of unique about them, is that they're really relevant to studying a wide range of particle numbers. So you can have 2 atoms in your resonator, or you can have 10 to the 5 atoms in your resonator. And depending what you're trying to do, this larger particle number is interesting if you want to use this for enhanced precision measurements. The small particle number in building up is potentially interesting for highly controlled quantum simulation experiments. Okay, so having atoms interact in a way that is mediated by light is already something that has been explored for applications in entanglement enhanced metrology, but also actually in the sphere of quantum simulation. It's been possible in similar physical systems to study supersolidity. Ben Lev is working towards applying these non-local cavity-mediated interactions to study spin glass physics. One of the things that sort of typically has been done in these types of systems, the sort of standard approach, is, well, we're going to use light to generate the interactions, so we may as well also get information out about our system by measuring whatever light leaks through the end mirror. And that's great if what you care about are collective properties of the system, like the collective magnetization. But one of the things that we kind of wanted to add to this is to be able to really study the dynamics of the system in real space, to be able to ask questions about how information spreads. Basically for any of the applications I described at the beginning, you need to be able to sort of look and say, what state are the spins in? Okay. So the experimental setup that lets us do that looks like this. It consists of sort of 2 mirrors end to end, about 5 centimeters apart. So it's really sort of macroscopic resonator with a standing wave of light in between that allows us to trap the atoms. So the atoms are trapped in sort of pancake-shaped wells of an optical lattice between these mirrors. And so if you sort of take a picture, you're going to see a cloud of, that's about sort of millimeter scale of these atoms. And the key thing is that we arrange these mirrors in such a way that even though they are far apart, the optical mode comes almost to a point in the center. So we take these 2 mirrors, we separate them by almost twice their radius of curvature, and but it's not separated by 5 centimeters, it's separated by 5 centimeters minus 50 microns. And that's crucial because you need to back off a little bit from this concentric limit to even have a stable optical mode at all. And when you do, you have something where the light comes to something like a 10 micron focus in the center, and the atoms are strongly coupled to the photons, but at the same time, the mirrors are far enough away that you can take pictures of what's going on inside. Okay, so that's what that looks like. Of course, that's part of some larger apparatus that was built by some very enterprising graduate students. So if they correctly align all of the optics, and their advisor doesn't misalign the optics, and Stanford doesn't turn off the air conditioning and let the optics drift, then they can proceed to use this apparatus to make the atoms interact. Okay. And so I gave you sort of a cartoon picture earlier of turning photons into spin excitations and spin excitations into photons and back. In practice, we do this in a way that we can control with a laser field. So again, if I imagined a pair of atoms, I would turn on a laser field that drives a process where an atom absorbs a photon from this laser field and emits a photon into the resonator, and that photon can be reabsorbed by another atom. We generate pairwise spin flip processes, and the nice thing about this is we have a lot of control because there's a laser field that can switch the interactions on and off. If I look carefully at sort of this interaction mechanism, you'll see what I want to do is not have a resonant process where I flip a spin and put a photon in the cavity. I want the only resonant process to be the one where that photon gets reabsorbed and flips another spin. Okay, so this process will operate at a place where the situation where we put a photon in the cavity is only a virtual process. And by adjusting the laser frequency and deciding whether we're red or blue detuned from resonance, that will also determine, for example, the sign of the interaction. So that will also be something that's optically controlled. Okay, so let's put this to the test. So here's an experiment where we've kind of initialized a system where most of the atoms are in the spin down state, but in some region here we generated some spin excitations. We turn on this laser field and sort of watch what happens. Okay, so here's as a function of time, we're looking at, so each row here is kind of a picture of the number of spin excitations or the density of spin excitations in some region of the atomic cloud. And we're watching how that evolves as a function of time. One thing you immediately notice is these spin excitations kind of hop over from this region of the cloud to somewhere completely different. And then they start to come back. Okay, so it immediately jumps out at us that there's something very non-local going on. So it's not that these excitations sort of travel outwards, diffuse outwards. They suddenly sort of hop to somewhere completely different. Okay, if we look versus time, we can see some oscillations. So there's something coherent going on here, which we like. And one thing you might ask is, why do the excitations suddenly decide to go over here from, let's say, region A to region B? So that's something you couldn't have known without me telling you, that something we can actually separately measure in this system is how strongly are the atoms coupled to the light field as a function of position. So in this particular experiment, actually, it turns out the center of the resonator is here. The atom-light coupling sort of has some spatial dependence, and as a result of that, what's happening here is that the atoms immediately, when the spins flip, the excitations immediately go to sort of the most strongly coupled region of the resonator. So somehow the dynamics are no longer set by physical distance, they're set by the structure of the light field. Okay, so it turns out that we can actually kind of model what happens here quite well. And essentially what goes into this model is to say that I can kind of view the spins as coupling to the light field via a Faraday effect. So this is essentially something where I have a magnetic medium that rotates the polarization of light. So actually the magnetization affects the polarization of light, and the light acts back on the atoms. And that model allows us to predict these dynamics quite well. So I'm happy that I can predict and model this. What I don't find so satisfying about that is that I've given you a very sort of classical picture for what's going on. So we wanted to ask, is there something a little bit more quantum mechanical that we can start to see in this system? And to give you some illustration that this classical picture is not the full story, I'm going to tell you one more thing that I kind of swept under the rug before. So I kind of pretended so far that these were spin half atoms, but it turns out actually this is a spin 1 system. So each atom has 3 internal states that I'll call the -1, 0, and +1 state. And you can now start to ask questions like, what if we initialize this system by putting all atoms in the 0 state? Okay? So if all atoms are in the 0 state, there's no net magnetization to the system. And so naively, you might say that by this argument that it's the magnetization that couples to the polarization of the light, maybe you would think nothing should happen. Okay? So we can ask the question, if we turn on the light field with all atoms in the 0 state, will anything happen? Okay. So here's the experiment. We put all atoms in the 0 state, we turn on the light field, and indeed, actually something rather interesting happens. So this is basically showing 100 repetitions of the same experiment. And again, we started with, and in each iteration of the experiment, I will take pictures of the atoms in each of the 3 states. Okay, the first thing that jumps out is that sort of, there are large fluctuations, but what we often see is that there are some atoms in the -1 state, and whenever there are atoms in the -1 state, there are also atoms in the +1 state. So there's some process going on where we can take a 0 atom, flip it into a -1 atom, and at the same time flip another 0 atom into a +1 atom, and this has to happen in a correlated fashion. And okay, so the interpretation, this is actually very similar to some physics that's been seen in systems of ultra-cold atoms that are directly interacting via collisions. So I can have atoms of spin 1 where I have 2 zero-state atoms really literally physically collide and turn into a +1 -1 pair that conserves the magnetization. And that process actually, known as spin mixing, has been used to generate highly entangled states where one has essentially precisely the same number of atoms in the +1 and the -1 state. So if I were to sort of represent restrict myself to looking at the +1 and -1 states, I could sort of represent this as a state with a well-defined number of particles in each state, but absolutely ill-defined phase. So there's a way to sort of visualize this as a ring on a sphere. And it turns out that this state is a resource for precision measurements very near that fundamental Heisenberg limit that I mentioned earlier. So this is a process that's been seen in these Bose-Einstein condensates. I can also think of it a little bit like if you're an optics person generating correlated pairs of photons. The key signature of this kind of this pair creation process, one of the key signatures, is that the system really is unstable to the formation of these pairs, and one expects some exponential growth in the population. And actually that's something that we also see in our experiment when we initialize the system in the 0 state, turn on the light, and watch how population in these two + and -1 states grows. We see this exponential growth in population until it saturates. That's a signature of this pair creation process. Okay. What we would like to do is also ask questions about not only how much does the total population grow, but how well defined is the population difference between these two states. That is something that we will look at more carefully, that will allow us to actually assess is there entanglement in the system and how strong is it. So that's still on the to-do list. But why do I think this is interesting? So sort of on a practical level, these interactions that are controlled by light are sort of orders of magnitude faster than the collisional interactions in Bose-Einstein condensates. But also the fact that they're controlled by light means that I can have really sort of these interactions happening between atoms that are, if I want, a millimeter apart. And more generally can start to ask the question, given that light is controlling the interactions, can I use it to have control over, for example, the spatial structure of the interactions and the spatial structure of the resulting correlations? Another kind of neat feature, I sort of suggested to you earlier that these optically controlled interactions can be ferromagnetic or anti-ferromagnetic. That's something you can choose just by the virtue of the frequency of the laser light. So actually in systems of ultra-cold atoms, one often just has to choose a different atomic species and build a different machine to study ferromagnetic or anti-ferromagnetic interactions. Our system is one where one should be able to sort of have that be a knob that is controlled simply by the laser field. More generally, to start to kind of explore the phases of both this system of spin 1 atoms, but more generally some of the problems I showed you before, we'd love to be able to start taking advantage of this optical control of aspects like not just the sign of the interaction, but perhaps the form of the spin-spin interaction. So I showed you that we can make the spin excitations hop, this kind of flip-flop process. I also suggested earlier that for some of these optimization problems, maybe you'd like to be able to have a different form of interaction where you care whether the z components of the spins are aligned or anti-aligned, and that determines the energy. So that would be called an Ising coupling. And eventually, you'd also like to be able to start to explore how the spatial structure of interactions, how the graph of interactions determines how quantum information spreads, coming back to this question of can we make it spread exponentially quickly, for example. So I want to take you through sort of a little bit of a brief tour of a couple things we're currently doing in terms of starting to being able to sort of access these different knobs. So just to give sort of one example, we can start to ask, can we control whether we have these flip-flop couplings, spin excitations hopping, or interactions between the spin excitations, which I would call this Ising coupling, JZ. It turns out that that is controlled simply by the orientation of a magnetic field relative to the axis of the cavity. So in sort of condensed matter systems, you sort of need to choose a different material if you want to change the form of the couplings. Here it's the orientation of a magnetic field. And again, that comes from the intuition that when I sort of label the different spin components, I'm referring to the Z component as the component along the magnetic field. And the nature of the interaction is that the component, so the component of the magnetic field along the cavity axis will determine which spin component couples to the polarization of the light. Okay, so here are some data showing that just by tuning the angle of a magnetic field, we can tune the form of the couplings in this Hamiltonian. And it turns out just by flipping a laser frequency, we can actually control are the interactions ferromagnetic, that would be the red, or anti-ferromagnetic, blue. So concretely, actually, just to show one more nice picture, the way that we measure these interactions, if we want to measure, for example, not just this flip-flop process of the spin excitations hopping, but see that we can also generate these Ising couplings, we can do something like initialize a system where spins in one region of the cloud are pointing down, spins in another region are pointing maybe along the plus x and the minus x direction, and whereas earlier we looked at spin excitations hopping, now we can ask, for example, this particular Hamiltonian I've shown means that the spins, if I have some spins pointing along Z, then any other spin should start to precess around those spins. In other words, any spins that point along Z sort of form an effective magnetic field about which the other spins precess. And so just by taking pictures, we can measure any component of the spin. So for example, we can measure the phase of the spin precession as a function of time, and to map out the strength of this Ising form of interaction. So actually here are two experiments where we've done that with the laser tuned either to make the interaction ferromagnetic or anti-ferromagnetic. And okay, so I find it hard to sort of read off these color plots, right? There's something where the phase is changing. If you want to see in which direction it's changing, we can also sort of turn this into a 3D animation, and you'll see, yes, indeed, the spins are precessing about that effective field formed by the green spins here, but also you can directly see that when I changed the sign of the laser detuning, so I changed some aspect of my laser frequency, and I was able to change the sign of the interaction. That's evident by the fact that these guys are turning clockwise, these are turning counterclockwise. Okay, so we have sort of a couple of knobs there that are sort of, not things you would find necessarily in magnetic materials as something you can just switch with a button, but that we can do in the lab with these optically controlled interactions. One of the reasons I kind of like this possibility of switching the sign of the interaction is that when you have a system that is purely a spin model, so the only sort of thing that enters into the Hamiltonian are the spin-spin interactions, then changing the sign of the interaction is, if you think about the Schrodinger equation, the same as actually changing the direction in which time flows. So you can ask questions like, could you change the sign of the interaction and have a system evolve forwards and then evolve back to its initial state? And it turns out that asking that question is actually something where you might imagine that's something that's probably hard, actually, right? Making the system evolve back to its initial state. But that also means that potentially this type of a scheme can be used, on the one hand, to very sensitively detect a perturbation that might happen between the forwards and backwards time evolution. If you understand your system well, this type of scheme could be a tool for sort of quantum-enhanced sensing, taking advantage of some complex correlations that develop in the first part of this evolution. And on the flip side, if you don't understand your system well, testing how sensitive it is to perturbations can tell you things about how chaotic is the system, and it turns out that that type of a measurement is one of the techniques that has been applied to probe this process of quantum information scrambling. So we've run the sort of runtime forwards and we've run it backwards, but we haven't put all of these ingredients together, but there are compelling reasons to eventually do so. Okay, so I showed you these interactions that have a number of kind of fairly unique features. They're non-local. I showed you that we see dynamics that are driven by quantum fluctuations and that we think should give rise to entangled states, to be verified still in the experiment. And we have quite a wide range of control over the interactions, ferromagnetic versus anti-ferromagnetic, the form of the couplings, largely benefiting from the fact also that we can design the interactions with light. So where is this going? So really, the kind of a broad goal in the field is to get closer and closer towards the ideal of sort of what I would call a programmable quantum simulator. So something where we really can, taking advantage of the control that we have with light, really design our quantum system, and that includes designing, for example, the positions where atoms are trapped, and there have been beautiful experiments making ordered arrays of atoms with single site detection, 1D chains, 2D lattices, Eiffel towers. If we did this at Stanford, we might have to make a Hoover Tower. But all of this is amazing single particle control, and it becomes most interesting when one can start to, you can imagine these atoms are optically trapped, so they're a few microns apart, right? And so actually the crucial thing to start to study quantum many-body physics is precisely how you control the interactions between the atoms. One direction is you control the pattern in which these atoms are trapped, and you have some local interactions between the atoms. And I'll say a few more words about local interactions before I conclude, but the other direction is you want to sort of say, well, maybe the pattern in which they're trapped is fairly simple, like it's a 1D chain, but I'd like to be able to control how the interactions between the atoms depend on distance. And so, rather remarkably, in principle, there's actually an elegant approach that ought to allow us in this cavity system to really dial in how do the spin-spin couplings depend on distance in more or less an arbitrary fashion. And so the idea is the following. So imagine I have this 1D system of atoms. Eventually we'd like them to be sort of individually trapped and detectable, which they weren't yet, but that's the natural direction to go. And now imagine that you sort of go back to this spin exchange process I showed before, but you do it in a magnetic field gradient, okay? So the idea is if I tilt my sort of, it's like a tilt for the spin excitations. I apply a magnetic field gradient, then this spin exchange process is not resonant if the atoms are far apart, right? There's an energy cost to a flip-flop in a magnetic field gradient. But in principle, it's possible to bridge that energy cost if I have two laser frequencies present, okay? So if the laser frequency, the difference between these frequencies matches the energy splitting at that in the magnetic field, right? Matches the difference in energy splittings for these two positions, then it should be possible for me to actually allow the spin excitations to hop at a particular distance. And so this is something that we have started to play with just in that simple kind of I shouldn't say simple, but in the pair creation physics I showed you before, where we start with a system of atoms with a spin 0 atom on each site, and allow the system to form these pairs of plus and minus 1 atoms. So in that system, if we had a magnetic field gradient and only a single frequency of light, then you would say the flip-flop process should be energetically allowed only if the atoms are on the same site. But when we actually now turn on the second frequency of light, we can start to see that these pairs of atoms can form actually at some finite distance, which shows up actually if we plot correlations between positions of the plus 1 atoms and the minus 1 atoms as some sort of off-diagonal correlation. And so this is kind of a first step in starting to turn on interactions to control the distance dependence of the interactions via the frequency spectrum of the laser field. So we want to push that to a higher level of control, start to do this in an array of atoms, and just to give kind of one flavor of what you can do with that. One of the dreams is to start to say, now can I build models where I would see this sort of exponentially fast spreading of information? And so just by sort of controlling which laser frequencies are present, I should be able to control on which distances spin excitations can hop. And it turns out, actually, you could imagine doing crazy things like saying, well, I'll let them hop to nearest neighbor sites, second neighbor sites, fourth neighbor sites, and eighth neighbor sites, but nothing in between. If you do that, if you do it in such a way that interactions still decay with distance, it's not so different from having a simple linear chain. It turns out if you were to let the interactions grow with distance, which you can do when they're controlled by light, the model would start to look more like effective, like as if distance were governed by distance in some sort of a tree graph. And it turns out that at some intermediate point, based on at least numerical simulations kind of in the semi-classical limit, it appears that this type of a model in fact gives rise to that fast scrambling behavior, so that exponentially fast spreading of correlations. This is at least an illustration that there are some pretty unique things you can start to do if you can pattern the interactions between the atoms with laser light. I briefly want to mention this. So one neat aspect of this system is that it could give this fast scrambling behavior. This limit where the system starts to look like a tree graph also offers some interesting connections potentially to exploring how gravity can emerge from quantum mechanics. And in particular, this tree graph is something that has been studied as a discretized version of anti-de Sitter space, so of curved space. And I learned everything I learned about this tree graph from Steve Gubser, who tragically passed away this summer in a climbing accident. But I just want to briefly mention learning about these, this new way of thinking about gravity as the geometry of this tree graph, and starting to connect that to what you might be able to do with cold atoms was one of the most sort of remarkable and fun scientific collaborations that I've had. So I encourage you to read more about that in our recent paper here. Okay, so I've talked longer than I wanted. Do I have time to briefly say a few words about one other physical system where we have interactions that are a little bit more local? Yeah, good. So I told you about crazy non-local interactions. In the last few minutes, I just want to tell you about another experiment we have in our lab, where we're actually building still optically controlled interactions, but of a slightly more natural character, like what you might find in the material, where so interactions will decay in some way with distance. And these are actually interesting if you want to maybe not build exotic models, toy models for gravity, but build model systems for, let's say, that offer analogies, let's say, to frustrated magnets in condensed matter. Okay, so let me just show the basic idea. Here we had interactions that were sort of mediated by virtual photons, right? Creating virtual photons in this cavity. Here we're going to have interactions that are mediated by virtually exciting atoms to Rydberg states. So if I have an atom in a high-lying Rydberg state, it's so polarizable it can interact over distances of many microns, which is large compared to the spacing in something like an optical tweezer array. Okay, so and the basic idea is we're going to have take these atoms and we're going to shine some ultraviolet light that, if it were resonant, it would excite the atom to a Rydberg state. We work in a regime where it is off-resonant, so the atoms don't actually get excited, but we nevertheless sort of mix in a little bit of the character of the Rydberg state, and this gives us a way of controllably turning on some effective interactions among ground state atoms. Again, an interaction we can easily switch on and off with a laser field. Okay, one way to think about this physically is that the light induces sort of an energy shift and a Stark shift on the atomic levels, and if there's another atom nearby, that Stark shift is suppressed by the impossibility of simultaneously exciting two atoms. So the way that this manifests itself is that if we have a collection of spins, and we, for example, prepare the system of spins with different initial tilts, so they're all in the same state, but it's tilted in some way. If more of the spins are up, we should expect the spins to process faster, and if more of the spins are down, we should expect them to process slower, again, because there's an energy shift that depends on the number of surrounding up spins. So this is, again, an interaction of this Ising type. Okay, so these are actually data. So this is a situation where we've prepared different possible initial tilts of these spin vectors and watched how the average magnetization processes, and it gives us a sort of a twisting. More spins up lead to a faster procession, more spins down lead to a slower procession. Just to show, right, this is not just an animation, these are real experimental data. And this is, okay, so it shows us, first of all, that we can generate Ising interactions in this system. And it's actually interesting because precisely this type of a twisting evolution is known to be one way of generating squeezed states that I showed you sort of other examples of before. But now with the possibility of doing this in a way where the interactions can be locally controlled by a laser field, and therefore you can start to sort of have a natural way of perhaps preparing arrays of entangled states in a way that lets you build quantum sensors with various features enhanced besides the precision. So I just want to briefly show, okay, so we can generate these interactions, we can spatially control them. So here's an example where the intensity profile of the laser is some Gaussian intensity profile. As a result, if we measure the phase shift as a function of the tilt, right? So the vertical axis here is the tilt of the spin vector, the color is the phase shift. What I've plotted on the sphere here is that SZ, the tilt-dependent phase at the center of the cloud. But more generally, if we look spatially, we can see essentially the color, the strength of the color tells us the interaction strength, and that's decaying in a way that is set by the profile of the light. Okay, so we have this optically controlled interaction strength. And one of the things I've sort of been excited to learn about recently from Chitra, who's a visiting scholar here and who's in the audience, is that actually the ability to optically control the interaction strength, and for example, to have an interaction strength that has some profile that looks like this, is an ingredient of a proposed scheme for realizing spin dynamics that can really be interpreted as giving rise to sort of an emergent black hole. So I won't go into the details of this except to say that if one can sort of alternate between a spatially varying and a uniform interaction strength, one can arrive at a situation where the quantum dynamics give rise to something that can really sort of rigorously be understood by an analogy to a black hole. Okay. That's one direction. Another exciting direction for this is that because you can control the interactions in time, you can start to study phases of matter that have no analog in equilibrium. For example, by alternating stroboscopically between interactions and, let's say, a transverse magnetic field. And so just to kind of illustrate, I should briefly say Vedika Kamani, who's here, is kind of a pioneer in this area who pointed out that, for example, there are new topological phases of matter that can arise if you can realize this type of a stroboscopic alternation between the interactions in the transverse field. So this is something that's, again, really natural to do in our system because we can control interactions with light. We can have an effective transverse field that's just controlled by microwaves. We can alternate them in time. So here's just one last experiment where we have essentially okay, I'll first show you an experiment where all we do is we turn the interactions off and we turn on a transverse field and we start to make the spins process, okay? That's not too surprising. But one way to sort of interpret this is telling me that if I have only this field, then the ground state of the system is all spins aligned along X. And when I prepare something that's away from the ground state, the spin procession, the spins will process around that, but the fixed point is the ground state. If I now start to turn on interactions, then I'll get some different dynamics. There are still 2 points now. There are now 2 points about which the spins process, and I can view those as coming about because the ground state of this system with interactions is one where the spins want to align a bit more, either along plus Z or minus Z. They don't care which. Okay, so there's a phase transition here from a paramagnetic state where the ground state is along X to a ferromagnetic state where the ground states are sort of tilted along plus and minus Z. And in our system, where the interaction strength is actually varying spatially, we can even cross this phase transition sort of in a single system as a function of position in the cloud. Okay, and this shows up by watching kind of the phase evolution of the spins, as a function of, again, as a function of the tilt, but also as a function of position in the cloud. And this is an illustration of a transition from having a single ground state, that's the sort of white region here, to these 2 new ground states appearing above a critical interaction strength in the cloud. So we have actually these ingredients of spatially varying interactions. We've crossed this phase transition between a paramagnet and a ferromagnet, which is sort of one simple part of a larger phase diagram that includes also phases that have no analog in equilibrium and require this ability to control the interactions in time. And so continuing to explore that will allow us to access quantum phases with no equilibrium analog. Okay, but also more broadly, we have here these ingredients of optically controlled interactions, either local for studying spin models that are of interest, for example, in condensed matter physics. Non-local for studying exotic models that might give rise to physics analogous to the physics of black holes. Non-local interactions that allow for encoding some of these optimization problems I mentioned before. And both of these systems also offer new tools for building entangled states with applications in metrology. So we're very excited about all of these directions, and I've probably spoken too long. And at this point, we'll just acknowledge my group, including particularly Emily Davis, who is the lead person on the cavity experiments, and Tori and Augie are the lead people on the Rydberg experiments I talked about today.
Questions? Everybody too cold? Yeah.
In the picture that you had at the beginning, when you do the whole thing from side B to A, like how far is that? How many sides and like how many atoms you have per side?
Yeah, so
Just thinking like,
the distance is something like 0.5 millimeter. And in that particular experiment, there's a very large number of atoms, so 10 to the 5.
is there a way to measure
and,
how
yeah.
far you are from a Bell pair?
So what would be interesting is, like you said, to really actually start to measure spatial, sort of the spatial structure of entanglement. And one way to do that would be something like asking how sensitive is the state? How sensitively can I detect some local perturbation? So kind of the sort of my intuition comes from starting with the case where I say I have generated some correlations that are across the entire cloud, right? And then you can make a state that is particularly sensitive to some rotation of the total magnetization. If you want to start to ask about local correlation, things like correlations between the left side of the cloud and the right side of the cloud, you can have enhanced sensitivity to something like a magnetic field gradient, or more generally, ways that you could start to probe the correlations are to ask about sensitivity to local spin rotations, right? So, but yeah, so I agree that starting to ask about spatial correlations in this system is something that is a really exciting direction, and one that's natural to go in with the tools of the sort of local addressing that we have and the ability to locally detect. So, yeah.
I think Leo,
Yeah.
do not want
So when you saw this spin exchange from one side to the other across
Yeah.
the cloud, the spacing was like 200 microns or 300 microns. I understand, was that set by the distortion of the cavity mode by the index of the atoms, or what's that? You said that that's...
Oh, sorry. You're asking about the spatial structure of the mode? No. Sorry, I
Why
missed.
was it 200 microns away?
That had to do with the fact that was, so one end of the cloud was near the center of the cavity where the atom-like coupling was strongest. And we initialized some spin excitations a few hundred microns away from the center of the cavity. And so the key point was sort of not the distance over which, we didn't program in the distance over which the interactions were happening, but we had a particular spatial structure of the couplings to the light, which in turn dictated that the excitations first went to that most strongly coupled region. Yeah.
Okay, one more question.
Correct me if I misunderstood, but I think you were talking about procession. You said spin up is different than spin down. Why?
Are you referring to the last part of the talk
Yeah.
where yeah, so good. So in the last part of the talk, we were generating an Ising interaction between the spins, which is to say we arranged the situation where the spins were processing faster if there were, let's say, more spin up atoms and slower if there were more spin down atoms. The way that this comes about is we have a situation where the light causes an energy shift of the atomic states. So I can think of that as coming about from having kind of perturbatively some process where I excite and de-excite an atom. But the amplitude for exciting the atom is actually suppressed if there are other nearby atoms in the same state, because it is impossible to excite both of them because the interactions within the Rydberg state are so strong. So basically what we start with is something where if you had two atoms in the Rydberg state, they would be, their energy level would be, their excited states would be pushed very high in energy. And that means that even if I have two ground state atoms close to each other, the sort of light shift for each of those atoms is suppressed by the presence of the other atom. Yeah.
An answer? No? Okay,
Yeah.
all right.
Oh.
Okay, we have
Yeah.
one quick.
Yeah.
So, you understated, I think, the amazing experimental techniques you must have to perform all this gymnastics. Do you see applications for this beyond the sort of very physics type experiments you're performing?
So I would say in terms of, yeah, so where are the applications? I would say one sphere of application is the one I mentioned of quantum sensing and metrology. So one direction that I'm excited by is, I mentioned there's already been work on generating entangled states that can enhance precision measurements. But what will it take to actually sort of do that in a way that would improve a state-of-the-art optical atomic clock, let's say? And it turns out one of the limitations has to do with the fact that the goal of the clock is basically that the atoms form as a reference. The transition frequency in an atom tells us basically, we calibrate the frequency of our laser compared to the transition frequency in an atom. And that laser, if we're not constantly feeding back to it, its phase is wandering around. And it turns out that one needs in those situations to be able to measure that phase very precisely, but also one would like to be able to track large deviations of the phase. And in fact, current clocks are partly limited by the fact that they have to sort of stop every so often and read out the state of the atoms because the phase has wandered by something on the order of 2 pi, and once it wanders by 2 pi, there is a fundamental ambiguity, and so you need to stop before then. Okay, so this is a long-winded way of saying it turns out that if you can make, for example, arrays of many entangled states, rather than just having a single one, you can basically have a measurement that simultaneously is very precise, but also has a large dynamic range because those separate ensembles can allow you to track sort of multiple different bits of the thing that you're trying to measure. So this is an example, I give this as an example where, first of all, there's an application for the entanglement, but also for the ability to really not just have kind of a single quantum state, but really some spatial control over the structure of the correlations. And, okay, so on the fundamental side, there's a question of how do you make those states, but practically those would be applicable to enhancing these clocks. And then I actually think the main reason for enhancing those clocks is that they're getting so precise that they can start to be used in tests of fundamental physics. So is that an application or not? I guess that's a matter of perspective.
Okay.
Yeah.
All right, well, let's thank Monika.